Hello again, everybody, and welcome to another Geo-Institute live stream. It is our second one of the year, and we are very excited today to kick off a new three-part series with Maccaferri. We'll get to that in just a moment. If you don't know this by now, I am Brad Keeler. I'm the director of the Geo-Institute, and of course, like I said a moment ago, we are really excited to have you with us this afternoon as we kick off the new year with some new content on the YouTube channel. If you don't know anything about the Geo-Institute, well, I always wonder, how did you get here? But besides that, after you watch this today, you should head over to geo-institute.org, and there you will find out so many things about us, including that we are a technical society with about 12,000 members, most of whom are geotechnical engineers and/or geologists, and that we are part of the American Society of Civil Engineers. If you like what you see today, here is a hint. You should click like, subscribe, and get notifications, and we will let you know every time we post something to the YouTube channel. You will notice, hopefully, that I am wearing a hockey jersey today. That is because we are mere weeks away from Geo-Congress 2024 in Vancouver. We hope you will be joining us up there. If you cannot, for whatever reason, well, we hope it's not by choice, but if you cannot join us for whatever reason in Vancouver, you can head to geocongress.org and find information there about live streams that we will be doing from the conference. Final thing before we get to our exceptional content today. Carl Terzaghi is here with us watching. We have just a few Carl Terzaghi bobbleheads left. No joke, less than 10 people. If you would like one, you know what to do. Head to geoinstitute.org, donate $96 or more to student programs, GI student programs, and we will send you a Carl Terzaghi bobblehead as long as you live within the United States and Canada. Now, what are we doing here today? We have an exciting partnership with Maccaferri in 2024 to do a three-part live stream series. And joining us in just a moment is former GI employee. We don't do many live streams with former GI staff. Mike Koutsouras from Maccaferri. He's going to talk to us today about simple drapery systems. Here to tell you a little bit more about that and to introduce Mike and to serve as your exceptional moderator today is Sebastian Derringer from Cornforth Consultants. Sebastian, this is your show.
Hello, everyone. My name is Sebastian Derringer. I am a certified engineering geologist and work at Cornforth Consultants Landslide Technology based in Portland, Oregon. Today, I have the pleasure of introducing Mike Koutsouras to you all. Mike is the Geohazard Mitigations Business Unit Manager of North America for Maccaferri Incorporated. Mike has a bachelor's in science in civil engineering and from the North Carolina State University and a master's degree in civil engineering from Georgia Institute of Technology. Mike is a geotechnical engineer with over 34 years of experience and has authored and presented several technical papers at various industry conferences throughout his career. For the past 6 years, Mike has been an officer of the Association of Geohazard Professionals and chairman of the ASTM Subcommittee for Geohazard Netting. Mike, the floor is yours.
Okay, good afternoon, everyone. Let me go ahead and share. Okay, hopefully everybody is now seeing the screen. Good afternoon again. My name is Mike Koutsouras. I'm the Geohazard Mitigations Business Unit Manager of North America for Maccaferri. For those of you unfamiliar with Maccaferri, the company was established 144 years ago. Currently has over 3,000 employees worldwide and services over 130 countries. In addition to having invented the Gabion basket, Maccaferri has been manufacturing and supplying geohazard mitigation systems throughout the world for over 60 years and is recognized as a leading innovator and manufacturer of these solutions. I want to welcome you to our first geohazard mitigation webinar on simple drapery systems for rockfall mitigation. This webinar is the first of 3 geohazard mitigation webinars in which we will discuss the design, specification, and installation of simple drapery systems used for rockfall protection. Please look out for future ads on webinar number 2, where we will discuss how steel wire mesh is used as a flexible facing for pin drapery and soil nailing systems, and webinar 3, where we will discuss rockfall barriers and attenuators. These next few slides show some real-world occurrences. This large rock slide struck U.S. Route 64 in Polk County, Tennessee, back in 2009. Following an intense rainfall event associated with a tropical storm. The slide obliterated and buried the roadway under 25 feet and 15,000 cubic yards of rock, soil, and debris.
Hollywood epic. We were warned that another slide could hit right where we'd been standing, but you don't expect this. Hollywood epic.
In this occurrence, rainfall had likely loosened the soil and rocks on the side of the cliff, causing boulders to come crashing down onto southbound Loop 360 in Austin, Texas.
Of the cliff to see if there's anything that needs to be cleaned up. Then in about a week is when they plan to bring in equipment and really pick up all of the debris from the rock slides sitting on the side of 360 like you see now. Now, if we're talking about the top of the cliffs, that is a different story that we want to show you right now. And that is to remove rocks that may fall. Think larger rocks that could pose a bigger problem. Things that look like they may shake loose. Now, that would require TxDOT to coordinate with private property owners. A TxDOT spokesperson also told us something else that they may consider. We want to of the cliff to
these rockfall hazards can be very sudden and catastrophic without any warning. Here's another one just last month occurring in northern New Jersey.
More concerns tonight about the stability of the rocks on the spectacular Palisades in New Jersey overlooking the Hudson River. A rock slide after Sunday night's rain damaged several cars at a luxury apartment complex.
Well, tonight residents are worried about more rock slides and what can be done to protect them. Here's New Jersey reporter Anthony Johnson.
The rock slide was caused by the heavy rain we had Sunday into Monday. That's the conclusion reached by engineers. But residents living above the site believe increasing traffic is playing a part in causing the ground to shift.
There's been a large amount of heavy truck traffic in the area, cutting through all these streets to avoid traffic in other areas. And there is an increased amount of vibrations, which is easy enough to feel.
Antonio points to cracks in his retaining wall, which he recently repaired to show the ground is shaking.
And these cracks were not here last year.
A photo taken inside the Dutchess apartment complex on River Road, just below the cliff, showed just how dangerous this could have been, with rocks landing in the building. Mud and rocks also covered vehicles parked in the back of the building. John F. Kennedy Boulevard.
And this one also just last month in Colorado.
Images tonight of a rock slide on Wolf Creek Pass. Look at this. CDOT sharing this photo of the damage. It's off Highway 160 between Pagosa Springs and South Fork today. And you can see the road really was completely covered in rock right there. Officials say the highway was closed for a while, but they were able to open a single lane. They want anyone to know head that direction. There will be delays and one lane alternating traffic.
All right.
Images tonight of a rock.
This occurred back in February of 2020. This rockfall event sent 3 people to the hospital after a boulder struck a car on the Monongahela Boulevard in Morganton, West Virginia. Possible rockfall solutions can be categorized into one of 2 methods. The first method is to control or contain the event at its origin, and the second method is to protect or intercept the event after its detachment. Conventional methods to contain or control a surface instability at its origin include rock scaling, simple and pin drapery systems. Soil nailing and rock bolting are used to control deeper instabilities. Methods to protect or intercept the geohazard include rockfall barriers, embankments and attenuators, and debris flow or shallow landslide barriers. Methods to control and contain the rockfall event vary depending upon the nature of the instability. For example, to mitigate against superficial instabilities, as shown on the left side of the slide, a simple drapery may be considered as a solution to control superficial instability of smaller sized rockfall, whereas a pin drapery system may be considered to contain superficial instability of larger sized rockfall. The key word to consider for a mitigation approach that might include a simpler pin drapery system is superficial instability. If the instability is deeper within the rock mass, as shown on the right side of the slide, a more comprehensive global stability analysis would likely suggest rock bolting is necessary if the solution requires control and containment, rather than allowing the rock to detach and intercepting the hazard. In choosing the right system for your project, it is also common to combine a simple drapery system with other mitigation systems, such as a pin drapery and/or a rockfall barrier, within the same scope of work to optimize costs and effectiveness. Choosing the right mitigation system requires the designer to consider its placement proximity to the detachment area of the hazard and its most effective placement location. Systems that are placed close to the detachment area are typically simple and pin draperies. However, hybrid barriers and attenuators might also be a solution to consider as well. Note that draperies are installed at a higher elevation than the detachment zone of the hazard, whereas hybrid barriers and attenuators are installed at a lower elevation than the detachment zone of the hazard. Rockfall barriers and embankments are systems that are installed far away from the detachment area and at a lower elevation than the detachment zone, and are designed to intercept the hazard. For these systems, it's necessary to determine the energy that the protection system must resist, as well as the protection system's required height and allowable deformation to keep the hazard from impacting adjacent people and infrastructure. Today we will focus our attention on the simple drapery system. We will present the application, design, method, system components, and properties that a designer should specify, and finish up with some practical installation considerations and case histories. Here's a neat photo of a simple drapery system at work on a highway in Colorado. This is a simple double twist wire mesh supplied by Maccaferri, commonly used by DOTs throughout the country. A simple drapery consists of a high-strength steel wire mesh system that provides a passive containment of the rock, meaning that it allows for the movement of the rock. It's the movement of the rock that mobilizes the strength properties of the netting. The goal is to control or contain the rock trajectory, reduce its energy and velocity, and force a sliding action down the slope, rather than allowing an uncontrolled free fall, resulting in an impact and rebound. A simple drapery will always be anchored at the top of the slope, but may or may not be anchored at the bottom. An open toe will require a catchment area at the bottom of the slope that would need to be designed to accommodate the debris, whereas if no catchment area is available, then the drape will need to be sealed at the bottom. The anchors provide no stabilization effect. They are merely there to hold the drapery system on the slope and contain any debris from encroaching on the adjacent structure at the toe. The function of the simple drapery is to let debris collect at the bottom of the slope. Looking specifically at the pros and cons of an open toe simple drapery, it's cost effective, very easy to construct and maintain. There's no excessive stress on the mesh and anchors since the toe is left open, and it can be designed for various size rocks with good control of the rockfall. There is maintenance that's going to be required, and you do need ample space at the bottom of the slope for catchment. Looking at the pros and cons of a closed-toe simple drapery, it's still very cost-effective and easy to install, can be designed for various size rocks with good control of the rockfall, and it's ideal if catchment space is limited at the bottom of the slope. Maintenance is required and a little bit more challenging than an open toe, and there can be large stress and deformations that occur at the toe. As with any civil structure, it's always better to engineer the system, taking into consideration the slope characteristics, size of rock, expected debris accumulation, geological considerations, and potential failure modes. Of course, failures can be costly and embarrassing. From a general design perspective, keeping things simple, we'll look at designing three main components. The steel wire mesh, the anchors required to hold up the mesh, and the cable required to hold the anchors. The goal, once again, is to control the trajectories, reduce the velocity and energy of the falling rock, and allow for controlled accumulation of the debris at the bottom of the slope. The design will verify first the mesh resistance required, second, the top cable resistance required, and third and fourth, the intermediate and lateral anchor resistance required. To perform a realistic design, we must first have some basic understanding of the site conditions and usually make some reasonable assumptions. Here are some basic input considerations: slope height and steepness, density and strength of the debris, volume of debris accumulation and or size of individual unstable rocks, and if snow or ice conditions may exist. We may need to make some reasonable assumptions to consider this additional load to the system as well. The design of a simple drapery system must consider both the weight of the mesh and the weight of the rock debris that loads the mesh at the bottom of the slope, creating a tensile force on the mesh. Here you see that as the debris accumulates at the bottom of the slope, the mesh strength must be designed to contain the debris accumulation. The stress acting on the steel wire mesh is a function of the slope inclination, the debris accumulation, and the friction between the debris and the slope. As you see in this chart, the force acting on the mesh is on the y-axis, and the height of debris accumulation is on the x-axis. So you see the force acting on the mesh increases as the debris accumulation increases, and the load also increases as the slope angle increases. The design method used is a limit equilibrium analysis, where we're determining the sum of the resisting and driving forces and determining a factor of safety. The resisting force includes the tensile strength of the mesh, which is transferred to the top cable and anchors. The driving forces include the weight of the mesh and the debris and snow loads. Looking closely at the free body diagram to the right, you may notice while the mesh weight is a driving force that must be resisted, it is also a stabilizing force critical to containing the unstable rock or debris and dampening the rockfall energy. The tensile strength of the mesh and the strength capacity of the top anchors must resist the load from the debris and snow and the weight of the mesh. The state of limit equilibrium is achieved when the sum of the resisting forces equals the sum of the driving forces. The effect of snow and ice is very real and can have a large impact on the tensile strength requirement of the mesh and pull-out capacity required for the anchors. The design of a simple drapery system must consider a realistic amount of debris that can be contained and consequently the stress in the mesh. The width of the debris accumulation, the mobilized deformation of the mesh, and the allowable distance to any adjacent pavement or structure, and the space needed for periodic maintenance must all be compatible. This slide shows tensile strength versus strain characteristics of many different types of mesh. As you can see, the load strain response of a steel wire mesh is unique and can vary greatly from product to product. The ability of a mesh to provide stabilization is determined by the mesh's ability to mobilize its strength under load. It's important that the strength of the mesh be mobilized within an acceptable design deformation. This would be a concern for a closed-toe simple drape. The greater the deformation of the mesh under load, the more debris that can accumulate at the toe of the slope. As more and more debris accumulates, the required tensile strength of the mesh would need to be increased. To control deformation under load and mobilize the full tensile strength capacity of the mesh, vertical high-strength steel cables may be woven into the mesh during the manufacturing process. The Federal Highway Administration has acknowledged that the inclusion of vertical ropes in addition to a top horizontal rope reduces the stress concentration on the mesh as well as along the top horizontal rope. With increasing the frequency of the longitudinal cables, higher tensile strengths are achieved at low deformations, and the reduction in stress concentration to the mesh and top cable is further improved. Maccaferri manufactures a composite cabled mesh, which consists of a double-twisted steel wire mesh and high tensile strength steel cables, which are woven under tension into the mesh during the manufacturing process. The pre-tensioned high-strength steel cables result in ultimate strengths that are mobilized at only 6% strain. The lower elongation under load results in less loading on the drapery system. The Maccaferri SteelGrid HR is manufactured with high-strength steel cables woven longitudinally into the simple double-twist wire mesh. These longitudinal cables can be spaced anywhere from 20 centimeters apart, which is our SteelGrid HR20, to 400 centimeters apart, which is the SteelGrid HR400. Our most common product used is the SteelGrid HR30, where the cables are spaced 1 foot apart longitudinally. These high-strength steel cables can also be inserted laterally as well as longitudinally. This is our RockMesh series of products. Our most common RockMesh products would have the longitudinal and lateral cables spaced 30 to 100 centimeters apart. RockMesh 3030, for example, which is shown in the photo, has the cables spaced 30 centimeters apart in both directions. Along with providing additional mass per unit area to dampen the rockfall energy, these RockMesh products have significant punch resistance necessary to absorb large impacts. The Maccaferri High Energy Absorption HEA cable panel offers the highest tensile and punch resistance of any product on the market and is commonly used in the most extreme conditions. It is manufactured with a single continuous length of high-strength cable wound to create a square grid net or panel connected at each junction with a Maccaferri patented double wire knot. The cable diameters range from 5/16 inch to a 1/2 inch, and the panel openings can be anywhere between 8 and 16 inches. So in the design of a simple drape, there is no one size fits all. Maccaferri's approach is to design the system based on the project conditions and provide the appropriate mesh to meet the design requirements. As you see here, Maccaferri provides a range of SteelGrid, RockMesh, and HEA panels with tensile strengths ranging from 3,500 pounds per foot to well over 12,000 pounds per foot. Note that as the mesh tensile strength increases, so does its mass per unit area. The mesh tensile strength and mass per unit area are important characteristics that provide resistance to rockfall. As a preliminary design guide, we can match a specific Maccaferri product to the rock size that would be contained. This, of course, would be a starting point, assuming no snow loads or otherwise unusual conditions. So SteelGrid HR40 400 where the cables are spaced 400 centimeters apart. Typically, that product can be used for rock diameters up to about 2 feet. And then as the rock size increases, we will manufacture the product with a more frequency of cables. This chart shows the effect of coating type and weight on the corrosion resistance of the mesh. The Maccaferri products are coated with a zinc aluminum Galfan coating, which provides better corrosion resistance than 100% zinc galvanization. Our products are also coated with twice the coating weight as other products on the market, which further improves its corrosion resistance. And for the most severe corrosive conditions, we can also offer a polymer-coated product, which can further extend the service life significantly over conventional products. Our standard polymer colors include gray, black, tan, and brown. These colors are often required for aesthetic purposes to blend with the natural rock environment, depending upon the geographic location of the project. For instance, the top photo is a tan product commonly used in California, whereas the bottom photo is a black coated product commonly used in places like Hawaii, Puerto Rico, and the Northeast US. Brown, for instance, is often used in places like Colorado and the Northwest US. Now that we know the loads acting on the mesh and the required strength of mesh that must be mobilized, we can look at designing the top support cable and anchor capacity at the top of the slope to support the mesh. Specifically, we need to determine the anchor strength to resist the shear and tensile loads, the anchor pullout capacity, and the anchor spacing along the crest of the slope. Theoretically, larger diameter and or longer anchors can be spaced further apart. So all the components and connections of the system must be weighed against practical and installation cost considerations. In designing the top cable, we determine a factor of safety based on the allowable design strength of the cable divided by the maximum tensile force acting on the cable. The allowable design strength of the cable is taken as the ultimate strength of the cable reduced by a factor of safety, and the maximum tensile force acting on the cable is calculated based on a catenary theory, which takes into account the lateral spacing of the anchors. In designing the anchor capacity, we need to look at the tensile and shear strength of the anchor element itself, the bond strength between the grout and the anchor, and the bond strength between the grout and the rock or soil. The contribution of each anchor is dependent upon the capacity of the anchor and the lateral spacing between the anchors. The anchor size is then determined by considering the working shear or tensile strength of the anchor and the shear or tensile force acting on the anchor. Dividing the working strength by the active force gives you the factor of safety. The anchor plays an important role because it must support the whole system. Its length must be deep enough to reach the stable section. The minimum theoretical anchor length is described in the equation shown, where L sub S is the minimum foundation length and L sub P is the length of plasticization. The minimum foundation length, L sub S, is a function of the diameter of the drill hole, the bond stress between the grout and the rock, and the maximum pullout force applied, calculated with catenary theory. The length of plasticization, L sub P, is the portion of the stable rock mass that loses its strength due to the bend deformation of the anchor bar stressed by a load. The values of L sub P depend upon the type of rock and range from 6 inches for hard rock, about a foot for weak rock, and 1.5 feet to 2 foot for weak, very weak, or highly jointed rock. It should be noted that the design anchor length should be field verified during the drilling operation to confirm the design calculations. In designing a simple drapery, Maccaferri offers several design tools, including the MacRO2 design software, a theoretical design manual if you wish to review and verify the computer analysis, product technical data sheets, product standard specifications, and typical drawings and details. Here's a quick look at the input screen of the MacRO2 design software. The user would input the rock slope characteristics, including the slope height and steepness, characteristics of the debris accumulation, and snow loading conditions. Then the user would choose the steel wire mesh to be analyzed. And for ease of use, the properties of the mesh are already hardwired into the program. Then the user would input the anchor type and spacing and the crest rope diameter. The program has hardwired the properties of the anchor and crest rope and has recommended safety factors. However, the user may override these hardwired values as necessary. Finally, the factors of safety for the design of the mesh, crest rope, and intermediate and lateral anchors are calculated and shown at the top, with the details of the calculations also presented down below, including the stress on the mesh, the maximum force on the anchors, and the minimum anchor diameter and length. Best results are achieved through analysis and experience combined. Even if the software allows a quick and simple calculation, on-site observations and experience are always useful to achieve a good design. So we would encourage you to give us a call and let us assist you. We have a group of very experienced professionals that you can lean on as a resource for your project. So please don't hesitate. Our services are complimentary. The performance properties of the system that should be incorporated into a design specification include the minimum required tensile strength and maximum elongation of the steel wire mesh, the mass per unit area and maximum opening size of the mesh, the minimum top cable tensile strength and diameter, the maximum anchor spacing at the crest of the slope, the minimum anchor shear, tensile, and pullout capacity, the minimum anchor length, and finally any durability and aesthetic considerations such as coating type, weight, and color. These are the basic elements of any good simple drapery specification, all related to system performance. Next, we'll look at some practical aspects of design and installation of the simple drapery. The first practical aspect of design is to select the appropriate mesh. Rather obviously, the larger the rock or greater the mass of debris that needs to be contained, the heavier the load acting on the mesh. And the higher and steeper the slope, the heavier load due to the weight of the mesh. In either case, the required tensile resistance of the mesh would increase. Next, we need to size the diameter of the top cable and size and space and space the top anchors. If the anchor spacing is too large, you can expect greater stress and deformation of the top cable and a lower level of safety if an anchor were to fail. Therefore, typical top anchor spacing is between 12 to 25 feet. For a closed-toe simple drapery, the bottom anchors are typically spaced 25 to 50 feet apart. The diameter of the top cable is usually between 1/2 and 7/8 inch, and more commonly 5/8 to 3/4 inch diameter. At the top of the slope, it's important to make sure the mesh extends to a higher elevation than the detachment zone, and that the anchors are founded in stable ground, with not less than 5 feet of free top area as a rule of thumb. The top anchors could be either bar anchors or cable anchors. The photo to the left is of a bar anchor, and as you can see, the force direction is primarily a shear force acting on the anchor. In the photo to the right, that of a cable anchor, you'll notice the flexibility of the anchor allows it to distort in the direction of the force, which is resisted by the anchor's tensile strength with a negligible shear component of force acting on the anchor. So unless otherwise required, we'll always use the double leg cable anchor for the top anchors in our simple drapery kits. Here you see some close-up photos of the cable anchor with the head cable threaded through it, or the cable anchor could be shackled to a tag line. Double leg cable anchors will provide better load transfer, negligible shear force, and larger drilling diameters. As mentioned before, the simple drapery system needs to extend above the rock detachment zone, and the anchors need to be extended into firm, stable ground. So it's essential to consider the location of property lines and easement limitations and the effect they will have on the necessary coverage and anchorage of the system. So there are alternative solutions for this case, such as a raised drape. Here are some slides showing the installation of a simple drapery system using a man lift. And in remote and difficult access areas, the mesh rolls may be attached together on the ground, secured to a helicopter, and flown into place. Here you see guys on the slope making the necessary panel connections. Depending on the type of mesh and topography of the slope, the mesh may be joined together by hog rings, special steel links, or lacing cable. Now we'll go through some case histories. In this particular project, Topsy Creek Mine, the slope ranged from 330 to 500 feet. The rock size was about 1 foot to 2.5 feet, and a free fall maximum energy of 500 to 800 kilojoules. The solution must consider two main aspects. First, they wanted low maintenance. And second, they wanted to make sure that there was no surface reduction of the working area at the bottom of the mine. So a simple drapery solution was determined to be the best solution for this project for several reasons. First, the high uneven morphology of the slope was not suitable for a rockfall barrier, for instance. So it's somewhat of a process of elimination. The rockfall trajectories were too high to be intercepted by a standard barrier. Thus, several lines of barriers would have had to have been installed. The slope gradient was too high for a rockfall embankment, and the space at the bottom of the slope could not be reduced. Rockfall embankments generally require a significant amount of space at the bottom of the slope. So that solution was eliminated. And the surface was just too big to install a cost-effective pin drapery system, which is an expensive system, requires a lot of drilling. So the most obvious solution was a simple drapery solution in this case. The Maccaferri high-strength SteelGrid HR30 was the product chosen with a 5/8 inch diameter top cable and 5/8 inch diameter double leg wire rope cable anchor, spaced 10 foot apart and with a length of 13 feet. Those are the general conditions for the solution. This next project was a simple drapery installed along Canyon Springs Road in Twin Falls, Idaho, to protect the road that accesses the golf course and several other recreational spots along the Snake River. Aesthetics was an important issue for the owner and the designer. In this project, approximately 28,000 square feet of SteelGrid HR30 was PVC coated black to blend in with the basalt. And in the background, you'll see a bridge over the Snake River, noting that from the bridge, the PVC coated black SteelGrid could not even be seen as it blended in so well with the basalt. Here are a couple of views of the top support detail. Note that the top support cable threaded through the manufactured loops at the end of the rolls of the mesh. Also notice that the top support cable is pulled away from the slope crest, a sufficient distance to ensure that the ground anchors are installed into solid ground. Here, you'll barely notice the installed PVC-coated SteelGrid as it blends in so well with the rock and is flush with its surface. You can see right through the black SteelGrid without even noticing it's there. This project is along the southern coast of Tutuila Island in American Samoa. The steep coral cliffs off the coastal highway had significant history of rockfall. The simple drapery solution included approximately 135,000 square feet of Maccaferri SteelGrid HR30. The near vertical cliffs ranged up to about 150 foot high on these 4 sites. In 2017, the Oroville Dam, the tallest dam in the U.S., suffered damage due to its main spillway. During widespread rainfall in California, resulting in its closure. Many of you probably remember this. During phase 1 of the repair work, Maccaferri supplied 60,000 square feet of SteelGrid HR400 to meet safety standards on the site. Work during phase 2 included the complete demolition and reconstruction of the upper portion of the existing spillway. High rock faces posed a threat to anyone working in the area, and so before the spillway construction could be continued, the narrow area between the cliff face and the service spillway walls required mesh drapery to protect the operations during construction. So in this case, approximately 120,000 square feet of Maccaferri RockMesh 3030 was used to protect the workers and equipment during day-to-day operations and provided the protection from rock disturbance as a result of demolition blasting. In this project, heavy rains had led to a landslide and major road closure along Highway 23 in Malibu, California. The 1.6 miles of highway remained closed until the mass of rock could be cleared and further mass movement stabilized. This resulted in a Caltrans emergency repair requiring 32,000 square feet of powder-coated cable nets, pre-attached to brown polymer-coated double-twist wire mesh. This project is in Northern California along Highway 96 in Happy Camp. This is a very active rockfall-prone area for Caltrans. The project included over 100,000 square feet of powder-coated tan RockMesh 3030. And in this project, to mitigate the rockfall along Makapu Saddle Road in Honolulu, the Hawaii DOT required approximately 45,000 square feet of Maccaferri RockMesh 3100. The product was polymer-coated black in order to provide greater surface life in the harsh corrosive environment in Hawaii and to blend in with the volcanic rock. This is another Caltrans project along a 2-mile stretch of I-80, just west of the California-Nevada state line, to prevent continued rockfall along the shoulder areas and roadway. Various sections of the project included flattening existing slopes, installing a simple double twist wire mesh drapery, and installing 279,000 square feet of the Maccaferri high energy absorption cable nets, pre-attached to a double twisted wire mesh raised drapery system. For aesthetic purposes, the HEA cable nets were powder-coated gray and attached to a polymer-coated gray double-twist wire mesh. And this is the same I-80 as that previous project in California, but this is on the eastern side of the country in New Jersey. Interstate 80 between New Jersey and Pennsylvania, heavily trafficked area, carries approximately 18.5 million vehicles per year. The existing rock cut areas result in safety hazards as evidenced by steep rock face, loose boulders and rock blocks, and have resulted in rocks toppling down and landing on the shoulder and roadway lanes. So this high rockfall risk combined with the high traffic volume was obviously important important concern for the traveling public and the New Jersey Department of Transportation. They implemented a simple drapery solution for the rockfall mitigation designed and specified by Haley and Aldrich, where 40,000 square feet of the Maccaferri SteelGrid HR30 simple drapery kit was used. And not too far from that site is Interstate 280 in New Jersey, also one of the most heavily traveled highways in the country, connecting I-80 with I-95 and providing access to the Holland and Lincoln tunnels into New York City. As the 6-lane highway passes through the densely populated West Orange Township, rockfall hazards also became a concern to the New Jersey DOT, which launched another rockfall mitigation project that consisted of a 90-foot high simple drapery. This simple drapery was again designed and specified by Haley and Aldrich, who specified the Maccaferri SteelGrid HR50 in this case, where approximately 150,000 square feet of HR50 was installed. Rock slides are also a common issue in parts of eastern and southern Ohio. The Ohio DOT identified nearly 40 locations in more than a dozen counties where slips and rockfalls are likely to occur in the near future. Among them was US Route 33, southeast of Athens, a section of the highway used by nearly 9,500 vehicles per day. At this site, a simple drapery system consisting of 135,000 square feet of Maccaferri RockMesh 2050 was installed. And finally, not to leave out our brethren in Canada, this final project is in Quebec, Canada. The Samuel de Champlain Promenade is a large park extending 4.3 kilometers along the St. Lawrence River. The development required a future railway line be positioned at the toe of a very steep rock cliff up to 100 feet high. And to mitigate the potential rockfall, a simple drapery solution consisting of 325,000 square feet of Maccaferri RockMesh 3100 was installed. And that's all I have. I'd like to thank you all for attending today's webinar. I hope you gained some valuable information. If you are interested in having more information on various products and applications, we can provide you with a Maccaferri Rockfall thumb drive that includes all our information. We also include technical publications, technical data sheets, typical drawings, product standard specifications for your use, as well as our design MacRO1 and 2 design software. So feel free to reach out to me directly by email, or you can find my information on our website, Maccaferri.com. Please look out for future advertisements for our next live stream webinar on March 19th. The topic will be on flexible facing systems for pin drapery and soil nailing applications. Personally, I have plenty of time for questions. Looks like we're short of our hour anyway, so if anybody has any questions, I'd be glad to answer them.
Mike, that was a great talk. Thank you so much for diving into the weeds of drape mesh and simple drapery that Maccaferri provides. As we're waiting for some questions to come in from the live stream, I have a couple for you, if you don't mind. Does high tensile strength wire improve the performance of mesh?
The performance of the mesh is a function of the load strain characteristics of the mesh, both in tensile and punch. So it's a function of the load strain characteristics of the mesh, not so much the wire itself. Performance is also a function of the mass per unit area of the mesh. So just common sense, you can kind of think that the heavier the mesh, the more it will dampen the energy, the rockfall energy. So those are the things that are going to affect the performance rather than the strength of an individual wire that is used to manufacture the mesh. So it's how the mesh is manufactured. Certainly the components that are used to manufacture the mesh have an impact on the ultimate strength of the mesh. But there's no direct correlation between the tensile strength of the wire and the performance of the mesh.
Gotcha. So that probably feeds in nicely between, or that probably has a direct correlation between the double twist or a single twist wire mesh. So the single twist probably has less capacity and the double twist has a higher capacity. Is that right?
The twist of the mesh is related to how the product is manufactured, how the mesh is manufactured, not so much about the components of the mesh. So a single twist, for those of you that are not following, a single twist would be much like a chain link fence. Everybody's familiar with a chain link fence where you have the wires just wrapping over each other one time. That's what we call a single twist. A double twist is our product, what we're known for, where the wire itself is twisted around itself twice. So the difference is, if you can imagine in a chain link fence, if one of the wires is breached by a rock, for instance, then it can unravel because the wires are very loosely just wrapped one over another in a single twist. So it can unravel. The mesh itself can unravel. And if the mesh unravels, then the mesh itself will lose its strength, both in tensile and in punch. The double twist wire, because it's wrapped twice around each other, if a single wire is breached, it will not unravel. The double twist will hold it in place, okay? And therefore the integrity of the overall mesh will remain intact. and it will not have an effect on the strength or the punch resistance of the overall mesh.
Gotcha. We do have one question from the live stream from Jude Vallon, who's asking why 5-foot maximum free at top for anchoring. I don't know exactly what that means, but to come to think about maybe your horizontal top rope, is there a anchoring requirement? Or do you understand that question a little bit better than I do, perhaps?
Could you ask the question one more time?
Why 5-foot max free at top for anchoring?
I think what the question is related to is the minimum distance that we would suggest bringing the drapery over the crest of the slope in order to anchor it into solid, stable ground. And that minimum crest distance should be 5 feet, as a rule of thumb. It may need to be more than that, but we would suggest at least coming over the crest 5 feet before anchoring it in.
That makes a lot of sense.
I think that was the question, but.
Gotcha. Another question from the chat from Krishna Chowdhury. You showed the anchors are installed on the top of the slope only. Can anchors not be installed along the slope holding the mesh as well? That may reduce the tensile zone.
Okay, so that will be covered in our next webinar. That's what we refer to as a pinned drapery system, where it's pinned along the face of the slope. So different application, definitely a more expensive application because there's more drilling involved. But we wanted to start out the webinar with the simple drapery system, which is the absolute most common system that's used for rockfall mitigation. It's the most common, it's the most cost effective. So the first line of attack would be, okay, can a simple drapery system work here? If the answer is no, then we start moving toward, okay, well, what then becomes the next most cost-effective solution? So yeah, stay tuned. We'll get to that one.
Looking forward to it, Mike. Another question from the chat from Lauren Sasanthan. What is the lifespan of the drapery system, or how often do they need to be replaced?
So that's a good question and a very loaded question. So it all really depends on the corrosive environment and what the product is coated with. What's the corrosive resistance of the product itself? So you could have product in Hawaii, and if it's not protected well, it will last a year in the extreme conditions out there in a place like Hawaii. Or Puerto Rico in certain parts. So that's why it needs to be determined what is the corrosive environment and what is the type of corrosion protection that's needed. In most cases, these systems will last well over 30 years. That's kind of a conservative estimate. If like I said, if it is a highly corrosive environment, we would always suggest a polymer coated type of product, which of course we offer, not much more expensive than the standard Galfan product. So that is a polymer coated product is what we might typically use in a place like Hawaii and Puerto Rico, and that's why Caltrans always requires also a polymer coated double twist wire mesh. There are cases where we have used stainless steel in places like Hawaii. So that is also an option if the conditions warrant it. Of course, a very expensive option, but that's always an option. But in most cases, the standard Galfan product in most parts of the country, most applications will last well over 30 years.
Matthew English asks, how quickly does the cost increase with more robust designs and more robust material?
Yeah, another good question. Really, the mesh itself isn't going to play as much of, isn't going to provide much increase in cost of the overall system. If you think of it in terms of materials versus installation, materials costs might be on the order of 1/3 to 1/5 the overall project cost. So installation is clearly the more expensive part of that equation. Installation is going to be greatly affected by the amount of drilling. So with a simple drapery system, there's not a whole lot of drilling. Whereas in a pin drapery system, there's going to be a lot of drilling. So the installation costs increase quite a bit. From the material standpoint, to go from mesh A to mesh B, the incremental cost is relatively negligible. I wouldn't say completely negligible, but it's a very small percentage of the overall cost. Does that answer the question?
I think so.
Okay.
And there's one last question before we wrap up from Jude Vallon. And this is a very practical question, one that comes up quite often. Should vegetation growth be behind the net be minimized to avoid tensile stress or punch through event? I think what they're asking is it okay to allow the vegetation to grow, or would you recommend to limit the vegetation growth behind a mesh panel?
We don't need to limit the vegetation growth. The vegetation growth can actually help stabilize the rock surface and keep the rock in place. So when there's less vegetation, the site is more prone to erosion and surface instabilities. So we have not seen where vegetation has affected the strength or has breached the strength of the mesh. So we would say, all in all, it would be more, the vegetation is more of a positive than a negative. And it from an aesthetic standpoint, of course, it also, helps to, bury the mesh. So really, everybody prefers not to really see the mesh. So the vegetation helps from an aesthetic standpoint as well. But from a performance standpoint, I would say the vegetation is more of a benefit than not.
That's great. Thank you, Mike. I think that wraps up our Q&A session. Thank you for your time.
Hey, thank you, Sebastian. Really appreciate it. Thanks, Brad.
Yeah, it was great having you back, Mike, and what a good presentation today. A good way to kick off the series. Sebastian, you did a great job moderating as well. And I put in the chat already, we will have 2 more live streams with Maccaferri on March 19th and April 23rd. You can register for those future events on our Eventbrite, and of course, they are free, just as today's was. Again, if you liked what you saw and you're here at the end, so you probably did, click like, subscribe, get notifications, and we'll let you know every time we post something to the YouTube channel. We have 2 more live streams before we head to Geo-Congress in Vancouver. They are next Tuesday and the following Tuesday after that. Next week, we'll be joined by Giovanna Biscontine and Don Leong, program managers from the National Science Foundation, to talk about the agency priorities and programs for FY25, especially looking forward to the proposal cycle for next year. And then in 2 weeks, we will have GeoStrata Extra, focused on an article from the current issue on the Turkey-Syria earthquake swarm from last year, which was a year ago today, I believe. So you want to look forward to that as well. You can register for both of those on Eventbrite. Mike, thank you again for doing this. This is fantastic and fun. You got some good questions.
Thanks, Brad. Really appreciate it.
Again, Sebastian, great job. Our producer today was Sean Herpelsheimer. We will see everybody next week.